week. Today's notes are on free body diagrams, so obviously we need to have a good understanding of the stuff we talked about last week and what forces are in order to talk about how we can start to diagram them. Playlist 1 is due tonight. These notes that we're starting today on free body diagrams are the first notes in playlist 2, which will be due at the end of this week. So again, to recap before we get into the new stuff, a force again is an interaction between two objects that results in a push or a pull. We talked about Newton's third law on Friday, which states that for every action there's an equal and opposite reaction, which we took to mean that forces are the result of simultaneous mutual interactions between two objects, and that these forces always come in pairs. And so if I, push a desk, the desk pushes back on me, type of thing. Okay, or if I push my foot back against the ground pushes forward on me. And so we were talking about how those mutual interactions give us these force pairs that are equal in magnitude and opposite in direction. Each force pair represents the same interaction. So talking about the interaction between you and the earth, it's the same force from two different perspectives. Okay, the Earth's gravitational field pulls down on you, you pull up on the Earth's gravitational field. And so you're describing it from two perspectives. Or I push on the desk pushes back on me. It's the same force because it's the same interaction. Or this one, if I pull on a rope, the rope pulls back on me. And we can identify or classify any of these examples that I've just talked about because there are a list of types of forces that you need to be familiar with. And I had several of these on the screen last week. But we're going to start with the one that was on my screen just a second ago, pulling on a rope. Okay, that gives you the force of tension. You guys are going to want to know the abbreviations that we use for these, like tension force is F sub T. And it is the force within a rope, string, or even your arm if you start talking about like the actual anatomy of your arm and the muscles that are in there. You can have tension in those due to holding up or pulling up an object. Okay, F sub T for tension force. Gravitational force is also the force of an object's weight, but the abbreviation for gravitational force is F sub G, but this is the weight of an object. It always points toward the center of the planet. Whenever you're talking about Earth's gravitational field, it pulls you downward toward Earth's center. And so whenever we talk about our gravitational force, our Fg is the Earth's field pulling on our mass. It's what gives us our weight. Okay, so again, Fg is weight. It is the force due to your weight. It always points downward. Applied force is F sub A. It is the force from a person pushing or pulling on an object. It does not have to be a person, by the way. Applied force is kind of a catch-all term if we have a force that we can't really classify elsewhere. Oftentimes we'll call it an applied force, but it is usually, you'll label it usually in scenarios where somebody's pushing or pulling something. Normal force, F sub N, is the force that a surface pushes back with. It's always perpendicular to the surface. Right now, several of you are taking notes or you have your computers out on top of your lab table. There is a normal force of support from the lab table pushing up against your computer, pushing up against your notebook, but it's the support force for whatever objects you set on that desk. There's also a normal force from the chair pushing up against you, holding up your weight. Okay, so a normal force is a support force, and it's something that the surface pushes back with. It's always perpendicular to the surface. Usually those surfaces are like tabletops or floors or chairs, but I could also lean against a wall. And if I lean against a wall, then my normal force is perpendicular to the wall's surface. So it doesn't have to be a vertical force. It could be horizontal, depending on the situation. Frictional force or force of friction is a force that opposes motion that is parallel to the surface. It is the result of two objects rubbing against one another. So if you slide one object over top the other, you're going to have a frictional force that exists between the two surfaces as they rub past one another. The last one up here is spring force. That is F sub S, force of spring. And it restores a spring back to its original shape whenever it's been stretched or compressed. And it doesn't have to actually be a spring. It can be anything elastic. Because if you stretch a rubber band like this, the rubber band also wants to go back to its normal shape. If I let go, it will do just that. Okay, but that force that wants to bring things back to their normal shape, whether it's an elastic band or a spring or anything elastic, pulling it back to its normal shape is the spring force. You can calculate the spring force with the equation up there. The absolute value of the spring force equals the spring constant multiplied by the absolute value of the displacement of the spring. So it's F sub S equals K times X. Again, you'll notice it's giving you the magnitude of it with that equation. All right, there are two different types of frictional forces. So I mentioned friction just a minute ago, but in this course you need to be familiar with two different types of friction. We have static friction and kinetic friction. So we're going to start with the definition for static friction. Static friction is going to be friction that resists the motion of an object, keeping it at rest. This is due to the rubbing of particles. There is a maximum value that must be overcome to start motion. Therefore, we say that the force of friction, or force of static friction rather, is less than or equal to the coefficient of static friction times the normal force. This variable that you see up here, let me turn on the little highlighter laser pointer. This one right here is called mu. Mu, it's a Greek letter. Mu is the coefficient of friction. This specifically is the coefficient of static friction. You'll have a different one here, mu sub k. But again, force of static friction is less than or equal to the coefficient of static friction times the normal force. Right now, your desk is stationary in this room, okay, and it stays in that position due to static friction keeping it there. If you push against your desk just slightly, it doesn't go anywhere, okay, and it's because of the, again, on the kind of molecular, maybe not even that, but microscopic level, what appear to be smooth surfaces actually aren't really as smooth as they appear. And so they'll kind of interlock with one another whenever you're talking about all of those little imperfections on like the feet of the table and the floor. And it makes it so that it's kind of hard to move the desk or to get it moving. That's your static friction. Kinetic friction, on the other hand, is the friction that exists when the object's moving over the other one. So static friction, here you're at rest, and again you can see this microscopic level where you have these kind of more jagged surfaces, if you were to look at them really up close, that kind of lock into each other. But once you get it moving, it's a little bit easier to keep it going. Okay, and that's kinetic friction. So static friction keeps it at rest. If you push hard enough to overcome static friction and you get it moving, you actually don't have to push as hard after that. Okay, kinetic friction exists when the object is in motion. It's the result of the rubbing between the particles that are passing over the surface. And now you can see that my force of friction, my force of kinetic friction rather, is equal to my coefficient of kinetic friction times my normal force. Again, static friction takes more force to overcome than kinetic friction. Once you overcome that and it's in motion, it doesn't take quite as much force to keep it in motion. Okay, so again, two types of friction. Yes, sir?
Is the letter next to the mu, you said?
Mu, yes.
Is that the spring constant?
No. It's the coefficient of friction. So this right here, this mu is the coefficient of friction. So mu sub S is coefficient of static friction. Mu sub K is coefficient of kinetic friction. All right, so again, we looked at all these a second ago. The only other thing I wanted to go back to was last week we talked about how we have these field forces and these contact forces. And pretty much everything is going to be a contact force in this class with one exception, and that is the gravitational force. Because the gravitational force, you don't have to have the objects touching. The Earth's gravitational field will pull on objects even if they're not on the Earth's surface. So this one was a field force. And I want to talk a little bit more about the gravitational force. Any object with mass has a gravitational field. However, our masses are so small in comparison to the Earth that we can ignore our own gravitational field and focus on field interactions between objects and the Earth. Okay, so we're just going to look at interactions between objects and the Earth's gravitational field. Okay, remember, gravitational force is a field force that results when an object interacts with the planet's gravitational field. That force of gravity is also called weight. Okay, I had a question last week when you guys were doing the schemas, and somebody asked if they could draw an arrow showing a force pair between the chandelier and the ceiling, which were connected through the chain in that particular example. But they were asking if they could draw a gravitational force between the two, because they both have mass. And technically, yes, they do both have mass. However, and that's what this is saying here, we are going to ignore our own gravitational field and only focus on field interactions between objects in the Earth. Okay, so although any two objects with mass technically have a gravitational force of attraction between them, because our masses are so small in comparison to the Earth's, that gravitational field would be negligible. You would not be able to notice any meaningful effect on anything because our masses are too small. So when we look at FG, it's only going to be between the Earth and the object and the Earth, but it won't be between like you and your pencil or you and your neighbor, because there's not enough mass there. But you can do it between you and the Earth. Okay, the Earth pulls down on you, you pull up on the Earth. That's still going to be a force pair. We're just not going to talk about your force of attraction to your desk, okay, or to other objects in the room. Now, I told you that the force of gravity is also called weight. Whenever we look at these interactions between you and the Earth, the force of the Earth pulling down on you is what gives you your weight, and it is Fg equals m times g. This is how you calculate it. You take your mass in kilograms and you multiply it by Earth's gravitational field strength, or gravitational acceleration, which on Earth is 9.8 meters per second squared. Okay, I know in our worksheets, in my open math, all of that, on your test you can use 10. Okay, if it's a lab setting, please go ahead and use 9.8. But that's the value for this equation. Fg equals mg, mass times 9.8 or mass times 10 will give you your weight in newtons. So you have to take your mass in kilograms and multiply it by g. Okay, all of this getting us to this discussion right here, free body diagrams. This is the topic of your notes today. So you need to know all the other stuff too, but it's leading us here. Free body diagrams are diagrams used to show the relative magnitude and direction of all forces acting on a system. The system is going to be whatever object or objects are being analyzed. Depending on the question you're trying to answer, you might have to define your system differently in order to solve for different things. Okay, there are certain ways you're going to have to set this up, and it'll make more sense as we practice it more. But you're going to need to identify your system in order to answer whatever questions we're asking you to find for the objects being analyzed. In your free body diagram, forces are drawn as arrows or vectors. The length of the arrow shows you the magnitude of the force. So larger forces should have longer arrows. The direction of the force acting on the system will be shown by the direction that the arrow is pointing. Okay, so you're going to show these arrows of differing lengths, and they need to be pointing in the correct direction to represent the forces acting on the system. There are two different types of systems that we can have in this course. The first is a no internal structure system, and a no internal structure system means that the internal structure does not have any effect on how the system moves on a macroscopic scale. Meaning it doesn't matter where I apply the force exactly, it's going to do the same thing. Okay, whether I push the book, at this point or whatever, if I'm pushing it along a surface. Okay, in this case, if the structure doesn't matter, we're going to draw our free body diagram using a dot for the center of mass because the structure doesn't matter. We're just going to show what the forces applied to the center of mass. However, sometimes it matters where those forces are applied, and if that is the case, you're going to use a rigid body diagram. In a rigid body diagram, the structure of the system impacts the object's motion, or how that object's motion results from the forces being applied to it. And so for a rigid body system, we draw the object so we can identify the point of contact where the forces are acting. For right now, all of our free body diagrams are going to be no internal structure. We're not going to do rigid body yet. We'll do them later on, I promise. They're going to come because there are different units where it matters exactly where you push on the object, specifically if the object's going to start rotating around something. Okay, but for now, we're just going to show the center of mass as a dot, and we're going to show all of the forces acting on the center of mass. Okay, as a rule, forces must be drawn originating from the system and pointing away. So we're going to start our arrows on the dot and then move them pointing away from the system depending on which way they're going. So we did an example with our schemas last week of this book on a table. So I'm going to go from a schema like this one to a free body diagram for, in this case, the book. Step 1 is to identify the system. I'm going to use the book. Okay, it says it up here, draw FBD for the book. Step 2, draw in X and Y axes. So I'm going to draw in axes so I can see the horizontal and vertical directions so that I can draw my forces appropriately. Because if they're perfectly vertical or perfectly horizontal, they should be on the axis. If they are not, if I have forces applied at an angle, I'll be able to show that with this grid, and I'll be able to show what the angle is. Okay, for this particular example, nothing's at an angle. There are only 2 forces acting on my book. One of them represented here by this blue arrow, one of them here by this green arrow. This one is the force of the table pushing up on the book. That's the normal force, and in my free body diagram, it is pushing up on the book. The table is supporting it perpendicular to the table's surface. So there's my normal force due to this interaction right here. The only other force acting on the book is the other part of this green arrow, the force of the earth pulling down on the book. That is the gravitational force. Okay, the force of the earth pulling down on the book. I'm going to draw in FG. Okay, and those are the only forces that I need, Fn and Fg. Okay, are these a force pair? Because they are equal and opposite to each other. Okay, however, we talked about force pairs on Friday. And in order for it to be a force pair, it needs to be between the same 2 objects. So this Fn and Fg, not a force pair. Fn is a force between the table and the book. There is another half. The book pushes down on the table. The table pushes up on the book. That's a force pair. This one doesn't show up in my free body diagram. Neither does this one. The force of the book pulls up on the earth. That's the other half of the gravitational force pair here. But it doesn't show up in my free body diagram because this force is acting on the earth, just like this one was acting on the table. So you're not going to see force pairs in a free body diagram. And Fn and Fg, even if they are equal and opposite, they are not a force pair. Okay? And oftentimes they are equal and opposite, still not a force pair. All right, let's try another example. A book is being pulled to the right across a desk from rest by a rope. Identify the system. I'm going to start by calling the system the book. Again, depending on what question I'm being asked, I may need to define it this way, I may not. It depends on what we're answering. Okay, I'm going to draw in my axes, my system as a dot, and I'm going to show all the forces acting on this. Again, I'm drawing it this way because the internal structure doesn't matter. Okay, it doesn't matter where I'm pulling it from. I'm just going to show the forces acting on the entire book all at once based on the center of mass. Okay, forces acting on the system. I know that I have the support force from the table, calls it a desk here, but the force of the table supporting the book, I know I have that, Fn. I know I have the force between the earth and the book. The earth pulls down on the book, that's Fg. Okay, I know that it's being pulled to the right across the desk, so the force of the rope on the book is to the right, that's Ft, tension. And then I know there's friction. Well, actually, it doesn't say that there isn't, so I'm going to assume that there is unless it tells me otherwise. So this is the frictional force that exists between the surface of the table and the surface of the book, Ff. Okay, so here is a free body diagram showing all the forces that I could draw acting on the book. On your AP test, there's a little note down here. It says AP test, no components. Okay, we'll talk more about this later when we have an example where there would need to be components, but if you have a force applied at an angle, there's a certain way that you have to make sure your free body diagram is drawn. And you have to find components to do some calculations, but they don't go in your diagram. We'll talk about it more, though, whenever we get to one. But make sure that you're only drawing in here the forces that are in the question. Okay, so this one we're good with. But if I have something at an angle, I'll talk about what this means. All right, here's a follow-up question. Okay, so the last one I drew a free body diagram for just the book. This says to redo the free body diagram, or rather, how would the free body diagram appear different than the previous one if I make the system the rope book system? So it's not just the book anymore, now it's the rope and the book together. And it does actually look different because if I include the rope as part of my system, then I can't show forces between the rope and the book on my free body diagram because those forces are now inside of my system. Whenever you draw the free body diagram, they have to be forces that are coming from outside the system acting on it. So if the rope is part of the system, that tension is now part of my system. And so if I look at each of these, this normal force is between the table and the book. That's okay because that's outside the system, the table is. Okay, earth and book, again, that's okay. It's outside the system. But this one is between the rope and the book, and these are both parts of my system. That makes this a force internal to my system, and it can't be in my diagram. Table, that's okay, that's outside, but this one can't be on there. So my free body diagram now looks like this. Okay, so again, depending on what information you have and what you're solving for, you might actually have to draw your free body diagram this way as opposed to the other one, or vice versa. Okay, if you wanted to solve for tension force, you would not be able to draw it this way because now you can't see that force. Okay, so it depends on what it is you're trying to solve for. All right, so this is relabeled FN, FF, FG. All right, guys, for the remainder of the class period, you're going to be working on playlist 1, which is due by 11:59 p.m. Playlist 1 includes the assignment 302 worksheet practice, which was the one y'all picked up in class on Friday. You're turning in pictures of the 2 pages there in My Open Math, and 303, which is a Google form. These things have to be done by 11:59 p.m. tonight. This is playlist 2 over here. You can start on that if you've already finished with playlist 1. If you guys have any questions as you're working, please let me know.